I'm thinking more U substitution. Yeah, all right. Let's start off with something like this. The integral of cosine of the square root of x plus 2 over the square root of x plus 2. So this one is really, no, let's just do it. So let's pick our U. I think I will say, at least in the beginning, if we're thinking U substitution, the choice of U usually should look relatively obvious. Like there's something that's just glaringly inside something else. Here, square root of x plus 2 is the obvious choice. It's actually in two places, in the cosine function and in the denominator. So we're going to pick U equal to the square root of x plus 2. You don't have to, but I think it's not a bad idea to rewrite it so that it's easier to differentiate. We've got x plus 2 to the 1/2 power. And then we do need to find the derivative of u whenever we're trying to do a u substitution. I think it's not a bad idea to write du dx equals the derivative over here, which is 1/2 times x plus 2 to the negative 1/2. I'm going to also think about the chain rule here just for a second to say I would multiply by the derivative of the inside, which would be 1. But just like if it was something, if that was like x cubed inside there, then there would actually be something to multiply by that would matter. And then usually you're going to jump straight to just putting the dx over there. So here's what we've got so far. We've got dx equal to 1/2 times x plus 2 to the negative 1/2 dx. And here's where I would really stress the importance of making sure that you deal with dx turning into something with du before you start replacing your things that look like u with u. Because if you go ahead and start writing this as cosine of u divided by u, you're going to miss something. Also, I don't know how to integrate cosine of u divided by u. It might actually be impossible. That's another good reason why we shouldn't start just throwing u's into our thing until we've dealt with dx turning into du first. How would I choose to do this? I would probably do it this way. I don't have a 1/2, so I'm going to multiply both sides by 2. So I have 2 times du equal to this piece here. X plus 2 to the negative 1/2, I could rewrite as 1 over the square root of x plus 2 times dx. And look, I exactly have that in my integral. It's right there. That is exactly equal to 2 times du. So I'm going to replace it with 2 times du. This is equal to the integral of some stuff, which I'm not going to write down yet, times 2 times du. And then finally, after I've made sure that I've appropriately turned dx into something with du, then I'm going to replace any remaining x's with whatever they're equal to. So here I'm going to replace the square root of x plus 2 with just u. And I probably would have written the 2 out in front, but I didn't. So we can think of this as 2 times the antiderivative of the cosine of u. We can anti-differentiate that and get 2 times sine of u plus a constant. And then finally, since it's an indefinite integral or an antiderivative, we have to end with the same variable we started with. We have to have 2 times sine of what u is equal to, which is the square root of x plus 2. Let's see. Yeah. Integration by parts.
Oh, yeah. Is that the same as?
Not at all the same. So yeah, so we can definitely get there as well today. But let's do a few more u substitution things. So, and actually I would say very generally, when you look at an integral and you're trying to decide how to anti-differentiate it, usually the places I go are first, can I try u substitution? Or does it make sense to try u substitution? And there's some kind of key things we look for. And then if that's not the case, usually I then try to look for like how to do integration by parts maybe. In fact, yeah, we might as well start doing. So we'll look at some examples where that kind of show us the differences between what might be the hallmark of a U sub versus what might be the hallmark of integration by parts. I will say very kind of blanket statement-y. If you have a function inside a function, you're thinking U sub because there's like a chain rule thing going on. If you have functions multiplied by other functions, you're thinking integration by parts because that's where you have essentially integration by parts is kind of like undoing the product rule, whereas U substitution is like undoing the chain rule. Chain rule is a function of a function. Product rule is a function times a function. So very broadly there, it's not exactly that, but it's pretty much that. So I guess before we can start comparing the methods there, we should talk about what integration by parts actually is. So integration by parts, we'll definitely still do use substitution today. Don't worry, it's not going away, but we'll talk about integration by parts here, which often is abbreviated as IBP. Integration by parts. So the idea here is that we would like to be able to integrate something like 2x times cosine of x. But as I've said, I think I said before, I'll say it again. The antiderivative of this is not x squared times sine of x plus c. Or more specifically, you can't integrate a product by taking the product of the antiderivatives, right? This is not equal to the antiderivative of x squared of, whoa, James, of 2x times the antiderivative of cosine of x, right? We cannot do it that way because of the product rule, right? If you took the derivative of this, the derivative of x squared times sine of x, using the product rule would be 2x times sine of x plus x squared times cosine of x. And that is for sure not the same as 2x times cosine of x. Integration by parts gives us a way to try to deal with how to integrate a product from these. And I should also just say off to the side here, we can't integrate everything, right? We are going to learn a bunch of methods of how to try to tackle a problem. But sometimes it's just going to be like, we tried a thing, we still didn't get there. I mean, hopefully not on your homework problems and your test problems, but like someone could just throw an integral out and like, well, maybe it'll try this and maybe it'll work. So you should get used to trying things that might not work and then trying something else. It takes practice, and some of the time you're just going to pick the wrong method. That's okay. So how does this work? Well, the idea here is that we're going to actually start with the chain rule. Sorry, chain rule, James. The which rule? The product rule. That the derivative of f of x times g of x is equal to f prime of x times g of x plus f of x times g prime of x. For whatever reason, people have decided to write this using u's and v's instead of f's and g's, which is terrible because my u's and my v's don't look that dissimilar. So I'm gonna write it using u's, f's, and g's first, and then I'll write it in kind of the standard way. So I have to remember what I'm doing here. Yeah, we're gonna anti-differentiate both sides. So the antiderivative of the derivative of a thing is just the thing. So if we anti-differentiate both sides, we're going to say that we have just f of x times g of x on the left, and it's equal to the antiderivative of f prime of x times g of x plus the antiderivative of f of x times g prime of x. Okay, well, I'm going to change the notation just a little bit. And also I should have some, sorry, I'm just trying, yeah, that's fine, sure. Yeah. I need some dx's there. So I'm going to remind you that another way of writing the derivative is that we can say that f prime of x is df dx. And f of x, sorry, g prime of x is dg dx, the derivative of g with respect to x. And we can not inappropriately think of these dx's kind of canceling out. And so the way we could write this is f times g, just doing away with the x's for a minute, is equal to the integral of g times df plus the integral of f times dg. Well, I know. He's like, what is he doing? This seems kind of weird. Don't worry, we're about to get to the place where things are going to make sense. I promise. I promise we're going to make it make sense. And then we're going to, we're going to isolate this and say that this is equal to this minus that. So that the integral of f times dg is equal to f times g minus the integral of g times df. And again, all we're really doing here is just kind of undoing the product rule. Written in the more usual way with letters that look too much like each other, we say the integral of u times dv is equal to u times v minus the integral of v times du. Here's what the process is going to be. We're going to have something we're going to try to integrate. And we're going to say, well, we're going to let one piece of that be u, and we're going to let one piece of that be dv. And then what we're going to do with that is we're going to find u and v and du, and then rewrite the integral as a new thing that still has an integral in it. But the new integral that you're going to get should be less complicated or less challenging to actually find the antiderivative of. That's the whole idea. Is with integration by parts, you're rewriting your integral as some piece minus a piece that's easier to find the antiderivative of. So let's actually use the example I started with. Let's say that we're trying to find the antiderivative of 2x times cosine of x. There's some guidelines for how you should pick which part is u and which part is dv. Very generally, we pick u to be something that's going to get simpler when you take the derivative of it. And you want to pick dv to be something that doesn't get more complicated when you take its antiderivative. So I would pick u equal to 2x because its derivative is 2. And if I picked u, oh my gosh, if I picked dv to be 2x, its antiderivative is x squared. And a higher power is more complicated. Whereas if I pick dv to be cosine, the antiderivative of cosine is sine. The derivative of cosine is negative sine. So picking dv to be the trig function is often the right choice because usually its antiderivative is not more complicated. So we're going to pick u equal to 2x and dv equal to the rest, including the dx. I will point out, these two things multiplied together should be everything inside your integral. Always, if you're doing integration by parts. Then we're going to find du. It's going to be the derivative of this, which is 2, multiplied by dx. We're going to find v, which is the antiderivative of dv. And the antiderivative of cosine of x is sine of x. And then we're just going to throw it all into the formula. Notice that when you actually write it out, you don't actually ever write u's and v's. You just write whatever you've chosen for u and v in the place of u and v. So we're going to say that this is equal to our u times our v, so our 2x times our sine of x, minus the antiderivative of our v times our du, which is our sine of x times our 2 dx. We could think of the 2 being on the outside of the antiderivative. It doesn't really matter here. But then we're going to anti-differentiate this easier thing now and say we get 2x times sine of x minus 2 times the antiderivative of sine is negative cosine. And then I would make that look nicer and say that it's 2x times sine of x plus 2 times cosine of x plus c. And that is the antiderivative of 2x times cosine of x. You could check it by taking the derivative, using the product rule for this part, and seeing that things will cancel out and you'll be left with 2x times cosine x. So that is an example of integration by parts. So then the question kind of becomes, well, how do you know when to do which? And really the answer is you kind of don't until you practice it a bit. Let's look at these two examples. Do I remember what my examples are? Yeah, okay. Sorry, I have to think for a second here. Yeah, let's say we have, so let's look at two integrals here. Let's look at this integral, the integral of x e to the x squared versus the integral of x e to the 2x. They look pretty similar. I mean, not really, but like, if you weren't looking that close, you'd be like, oh, those look kind of the same. One of these is definitely a u sub. One of these is definitely integration by parts. I can see that this first one is the u substitution because there's a good thing we can pick for u that's stuck somewhere else whose derivative is also in the integral. I'm going to pick u equal to x squared because the derivative of that, essentially, not worrying about any constant multiples, is also in my integral. The derivative of u is 2x. So du is equal to 2x times dx. And look, I almost already have that. I have an x times dx. All I have to do is divide both sides by 2 here. Let's say that du divided by 2 is equal to x times dx. And then we start replacing things. We start writing our integral as Integral of, well, the x dx gets replaced by my 1/2 du. I am going to put the 1/2 out in front because that's pretty standard practice. And then I still have to replace, so I'm going to underline the things I replaced. And then I still have to replace the e to the x squared, so that's going to get replaced with e to the u. Now we anti-differentiate. The thing I see people often forget about u substitution is like they do the replacing and then they just drop the integral symbol, which is, I guess, what it's going to look like that I do right here because the integral of e to the u is e to the u. But in general, you have to make sure that you actually then look at that and say, oh, what's the antiderivative of that thing that I'm taking the antiderivative of? Oh, in this case, it's kind of anticlimactic. It's just itself. And then we're not done. We have to plug back in that u is equal to x squared here. 1/2 e to the x squared plus c. This one is not a good candidate for integration by parts because if you let u equal x and dv equal e to the x squared, e to the x squared, I'll say it every time, is famously not antidifferentiable. You cannot find the antiderivative of e to the x. Doesn't exist. Don't try to find it. Questions about this one before we look at the other side here? All right. Looking at the other one. So here's what I would say about the other one. When I'm thinking about trying to anti-differentiate something, I'm usually going to think of, can I do a u substitution first? Because in my mind, it's kind of the easiest method to use if it works. So here I would think about, well, I still see there's a 2x trapped inside the integral there. So I could let u equal 2x. If I try to u sub, I'm trying a u sub here first. And then my du would be 2 dx. Okay, so 1/2 du would equal dx. But then when I start replacing things, it's going to be problematic because I'm going to have the integral. Well, I still have this x here. I have x. All right. Oh, sorry. I'm breaking my own rules. I should make sure that dx turns into du first. So I have a 1/2 du out to the side here. And then my e to the 2x becomes e to the u. And I've got this x left over. And sometimes when you have an x left over, you do what's called a back substitution, where you take your choice for u and you solve for x. And you say that u divided by 2 is equal to x. Here's the problem with this, at least in this example. I haven't really changed the nature of the integral at all. Yeah, I've multiplied it by a constant, but I'm really still left with a variable times e to a multiple of that variable. It's not any easier. I didn't make a dent, really. And often picking u equal to a multiple of x is not, right? We have already talked about how if your u would be a multiple of x, you can just divide by that thing at the end. But here, the u e to the u is problematic. I don't know how to integrate that. So that's telling me my choice of a u sub was probably the wrong choice here. I should probably have tried to do integration by parts instead. So integration by parts instead. There is an acronym for knowing kind of what order you might try choosing u in. So for integration by parts, I'm right over here. We typically try to let u equal a logarithm if we have one. I don't have a logarithm here, right? It's x e to the 2x. Neither of those are logarithms. So if we don't have a logarithm, then we let u equal, some people say it's an algebraic term. I like to use more words and say it's any power of x or whatever your variable is. Any power. X squared, x cubed, x to the 1/2, x to the negative third, x to the negative 1/2. If you have x to a power, that's usually what you want to try if you don't have any logarithms. And that is what we're going to let u equal here. I'll just finish off the list though. If you don't have either of those things, then you look for a trig function to let u equal. And then if you don't have any of those things, well, then you probably don't have a mixture of things, but you almost never let u equal e to the x or an exponential function. So in an integration by parts situation, right? There's other u substitution situations where it's totally fine to let u equal e to the x or whatever. But in an integration by parts problem, you almost never let u equal e to the x. So here I'm going to let u equal the x that's multiplying the e to the 2x. I don't know why I put a dot after it. Sorry, it's not meant to be there. And I'm going to let my dv be the rest, e to the 2x times dx. And again, I'm thinking about things being multiplied by each other when I'm thinking integration by parts. So I find the rest of the things. My du is 1 times dx. My v is the antiderivative of e to the 2x. This is exactly why I've talked about how we want to do these mini u substitutions without showing all the work. To anti-differentiate e to the 2x, you could do a u sub. You could let u equal 2x and then du is 2 dx and you get 1/2 e to the u, which is going to be 1/2 e to the u. Don't want to show all that work. I just want to know that, oh yeah, the antiderivative of e to the 2 times x is e to the 2 times x divided by 2. And that's really one of the primary reasons actually I've talked about that, is that these mini u substitutions come up in integration by parts often, and you don't want the problem to be that much more complex. You just want to be like, cool. So then we're going to write that our integral of x e to the 2x dx is equal to u times v. So x times 1/2 e to the 2x minus the integral of v times du. So minus the integral of 1/2 times e to the 2x times dx. And we're almost there. This first part is just 1/2 times x times e to the 2x. This next part is minus 1/2 times the oh my goodness, that was exciting. Go away. All right, well, that's fine. You can hang out down there, I guess. Just don't come back out. Yeah, a little bit. So anyway, the antiderivative e to the 2x, we just did it. It's again e to the 2x divided by 2. I'm gonna have to watch the video of that later. It's gonna be exciting. Plus c. When you do integration by parts, your answer should end up being some sort of product, so that if you wanted to check your work by taking the derivative, you would have to use the product rule. There is no analogous anti-quotient rule. If you had a quotient, you really just write it as a product by writing the inverse of the denominator. Yeah. Sure.
Well, it's like
Go ahead.
So I was stuck on a problem. I was wondering, would it be fine if I go over here, or
What's it about?
it's fundamental theorem.
Sure, we can talk about fundamental theorem. Do you have it specifically, or do you want me to make one up?
It's just what kind of confused me is like the integral. It's from like e to the x to negative e.
Okay.
And that's like what.
Sure. So let's look at something like, if we wanted to find, I'm assuming they're saying something like g of x is equal to the integral from e to the x to negative 8 of something terrible like the square root of t cubed plus 1 times sine of t, just to make it extra terrible. So there's my function, and it is a function of x, because if you were to actually anti-differentiate this, which you can't, and then plug in your limits of integration, the t's would go away, and you'd have some terrible function evaluated at negative 8 minus the same terrible function evaluated at e to the x. In fact, let's write that out for a second. Let's pretend that we know what the antiderivative is. We know that the antiderivative of f of t equal to this terrible thing I made up here is capital F of t, which is pretty standard notation when you're talking about made up antiderivatives. Or in other words, the derivative of capital F of t is equal to little f of t. It's another way of saying that capital F is the antiderivative of little f. Okay, so let's find g of x. So g of x is equal to the antiderivative of e to the from e to the x to negative 8 of the square root of t cubed plus 1 times sine of t. Well, the way we deal with definite integrals is by finding the antiderivative, which is right there, and then evaluating it at the upper limit minus the lower limit. So I would, oh, go ahead. Oh, was it negative 8? Yeah, sorry. My 8 became a 1 somehow. Apologies. Yes. It won't actually affect the answer, but yes, we should still use the same numbers. So then we're going to plug in our limits of integration. We're going to get f of negative 8 minus f of e to the x. Cool. So that's my function, g of x. G of x is equal to that. And now they're probably asking us to find the derivative of this. Right? That's what these fundamental theorem of calculus part 1 questions are almost always about. Find the derivative of this funky looking antiderivative. So here, if I start trying to find the derivative of g, f is some function. I plugged in a constant. I got out some number. And the derivative of some number is 0. If you get an antiderivative of something, but then you plug in an actual real number, you get some value. Maybe pi, maybe e squared, maybe, I don't know, other weird things, but it's a number that's not changing once you've plugged in an actual real number to it. And the derivative of something that's not changing, or the rate of change of something that's not changing, has to be 0. So the constant part almost ends up never mattering, right? That part just, you kind of ignore it. And then minus, we're going to take the derivative of this piece. So I'm going to take the derivative of capital F of e to the x. That looks like a chain rule. I have a function of a function. And when I'm taking the derivative of a function, I have to take the derivative of the outer function, leave the insides alone, and then multiply by the derivative of the insides. I should have picked something other than e to the x. Oh, well. I know that the derivative of capital F is my little f, which is the square root of t cubed plus 1 times sine of t. But now I'm plugging in e to the x. So that's going to equal negative little f of t, right? Because, sorry, f of e to the x, apologies. Right, I'm just replacing f prime, capital F prime with lowercase f. They are equal to each other. And then I'm still multiplying by the derivative of e to the x, which is annoyingly just e to the x. So there, I took the derivative there. And now finally, I'm going to plug in little e to the x to the lowercase f function that I actually know. If f of t is equal to all that, then f of e to the x is going to be the square root of e to the x cubed plus 1 times sine of e to the x. So I'm going to get negative square root of e to the x cubed plus 1 times sine of e to the x times e to the x. Now, that was probably the longest way possible I could have done that. You're not meant to do it that way. You're meant to know that the fundamental theorem of calculus says you get to plug in the thing. Well, I should back up. If it's in the bottom limit of integration, you get to do the negative of it. Back, let's just write out what it is up here. The g prime of x is going to equal negative. You plug in e to the x wherever you see a t. So I'm going to get e to the x cubed plus 1 times sine of e to the x. And then at the end of the day, you have to multiply by the derivative of the thing you plugged in, which happens to be e to the x. So that's the amount of work. They don't want you to do any work for these problems, really. They want you to just know that the theorem does the thing it does. So hopefully that kind of is a good example of how this works. All right. Back to some more U substitution versus integration by parts. Let's look at the integral of, which one do I want to do first? Let's do that one first. X cubed natural log of x dx versus the integral of the natural log of x divided by x dx. And I should have said something before I kind of started doing all this, but usually when I'm considering specifically integration by parts, but also U substitution, I'm only really bringing specifically integration by parts into play if I see what I would simply refer to as a mixture of functions, meaning there has to be two, usually exactly two, I guess there could be three, but two types of things of my list of late. There has to be a logarithm and a power of x, or a logarithm and a trig function, or a logarithm and an e to the x, or a power of x and a trig function, or a power of x and an e to the x, or a trig function and an e to the x. But if I just have powers of x, integration by parts is off the table. If I just have trig functions, no, it's really still kind of off the table. Usually, if you don't have a mixture of two or more types of functions, you really shouldn't be thinking integration by parts. U substitution is still very much in play, but integration by parts is not. So this first one here, there's not a lot of choices here, right? This looks like some kind of straight up multiplication. I mean, I guess, so if I picked u equal to x cubed in a u sub, my du would be 3x squared, and I definitely don't have a 3x squared anywhere, or just even an x squared. I mean, I do technically if you factor out an x from there, but then how would I have an x cubed left over? Or if I picked u equal to the natural log of x, my derivative would be 1 over x. Don't forget the dx, James. Again, not seeming like a good choice. I feel like I've kind of run out of options here for my u substitution. Also, I should just point out, we never want to pick just u equal to x if you're trying to do a u substitution, Because if you did, you would literally just be changing the variables to use and it would still look exactly the same. On the other side of things, it's totally fine and sometimes the exact right choice to let u equal x in an integration by parts problem. So just be aware. U equal x in u sub, no good. U equal x in integration by parts, often very good. Okay, so this one seems like it's not going to be a u sub. Let's try integration by parts. And according to my LATE acronym, LATE, what should I be picking u to equal from x cubed or natural log of x? Everybody. Yeah, the natural log of x, the thing that starts with L. Here's a good reason to, or here's a good way to know why. If you picked natural log of x to be the dv thing, then you'd have to anti-differentiate it. And at least, I think not yet, we haven't learned what the antiderivative of the natural log of x is, because it requires integration by parts. So the derivative of the natural log of x is 1 over x. The antiderivative of the natural log of x is something we'll do in a little bit. So that's a good way to know that you shouldn't be picking dv to be natural log of x. Here, dv is going to be our x cubed times dx. We finish off our little table here. We're going to let du be the derivative of the natural log of x, which is 1 over x, and then multiply it by dx. Our v is going to equal the antiderivative of x cubed, which is x to the 4th divided by 4. And then we put it all into the nice little formula. We have the integral of x cubed natural log of x dx equal to u times v. Doesn't matter what order you multiply them in, right? You could write natural log of x times x to the 4th over 4, or you can write x to the 4th over 4 times the natural log of x. And it's usually my preference to put things in front of the natural log of x instead of after the natural log of x. Minus the integral of v times du, which is x to the 4th over 4 times 1 over x dx. Again, the point of this process is that this new integral should get simpler. But to see that, sometimes that means you have to actually simplify the stuff inside of it before you can see that it's simpler. And we will. We'll write this as 1/4 x to the 4th natural log of x minus, I'm going to bring out the factor of a 1/4, but then x to the 4th divided by x to the 1st is just x to the 3rd. And that is something that is very straightforward to find the antiderivative of. So then we're going to get 1/4 x to the 4th times natural log of x minus 1/4 times, again, x to the 4th over 4 plus c. And I don't want to write another line, but you could simplify this to just be x to the 4th over 16. But probably don't need to. Yeah.
So.
Correct. That is an excellent observation. Yes. In the integration by parts, the derivative of u, we do not need it to show up in the integral. It might. It probably won't, though. But yeah, very good point. We do not need that. It's not something we really are looking for. Yeah. It really doesn't. I don't think I've heard anyone ever really say that before, but that's an excellent point to make. I'm glad you said that. Thank you. Okay. Over here, we do have a very, very good u substitution. And I will say this integral of natural log of x divided by x isn't meeting kind of all the criteria I usually look for. In that the thing I'm going to choose for u isn't really stuck in some other function. I'm going to pick u equal to natural log of x because the other thing that's true is the more important thing. The thing you're picking for u, it doesn't have to be stuck somewhere, but we would really, really like for its derivative to also be in the integral. And we're definitely getting that here. If we pick u equal to the natural log of x, the derivative is 1 over x, and then we multiply by dx. And if it helps us to see it, we can rewrite this as the integral of the natural log of x times 1 over x, instead of the natural log of x divided by x times dx. It's the same thing. I'm just trying to make it more obvious that, oh, look, this part here is exactly equal to what I just said du was. So we can totally rewrite this as the integral of du at the end, and then natural log of x is just what I said u was. We always have to make sure that everything with an x in it becomes something with a u in it if we're trying to do a u substitution. I should label things here. Great, we know how to anti-differentiate u to a power. Add 1, divide by the new power. The u squared divided by 2 plus c, which is going to be the natural log of x quantity squared over 2 plus c. And I guess technically there's this. I don't know why. I'm just old, I guess. I'm totally fine with writing sine of x quantity squared as sine squared of x. I really hate the fact that it's technically okay to write this as natural log squared of x. I think that's the stupidest thing I've ever seen, maybe. But I suppose that's appropriate notation. I know, I'm just very opinionated about this. I don't like that, but apparently it's correct notation. I would encourage you to write it like this because I think it looks better, but it's just me. Yes, I'm very biased against that notation. All right, so I think I have one more example. Yeah, I have one more. Yeah. Oh yeah, I know what it is. Let's do. Ooh, is that? Yeah, fine. We can do that one. It's gonna be kind of terrible. Yeah. How much time have we got? Okay, sure. So let's look at, say, this integral. How terrible do I want it to be? Not that terrible. X squared times sine of x cubed. You should be able to look at that and already know which method of integration you're going to use. Versus the integral of x squared times sine of x. In my mind, one of these is obviously a u sub. And it's that one. That one is obviously a u sub because the thing inside the sine function, if you take its derivative, is essentially that thing right there. Constant multiples notwithstanding. So we're going to do a u sub here. We're going to pick u equal to x cubed. Our du is going to be 3 times x squared dx. I'm going to do this one in a slightly different way, just for those of you that don't like doing it the way I've been doing it. So for me, I would say 1/3 du equals x squared dx and replace the x squared times dx with 1/3 du. But if you prefer solving for dx, here's how we can do it that way. We can rewrite this as du over 3x squared equal to dx. And then we can rewrite this as just replace dx with what we said it was equal to. Leave everything else alone for a moment. So you have x squared times sine of x cubed times du over 3x squared. And then you always want to try to cancel the variable below your du. So the x squared there cancels with the x squared there. And then replace any remaining x's with what they're equal to. So x cubed is equal to u. So we can write this as the integral of sine of u times du over 3. Or if you did it the way I wanted to do it, you would have had x squared dx being replaced with du over 3, and it would work out the same way. Then we anti-differentiate. We get 1/3 times the antiderivative of sine of u, which is negative cosine of u, plus c. And then we should write this as negative 1/3 cosine of x cubed plus c. Not too bad. And now for this other one. The reason I shake my head is because this one is going to require integration by parts twice, which is always fun. So when you're doing repeated integration by parts, the choices you're making should always be the same type of choice. Meaning, if you're picking u to equal a logarithmic thing the first time and you're doing integration by parts again, you should be picking u to be a logarithmic thing the second time. So the type of thing you're picking for u and the type of thing you're left choosing for dv should kind of remain the same throughout how many iterations of integration by parts you have to do. So here, I'm going to pick u equal to, let's see, LATE. I don't have a log, but I do have a power of x. I'm going to pick u equal to that power of x. And then my dv has to be the entire rest. A dx should be there. My du is 2x dx. My v is the antiderivative sign, which is negative cosine of x. Put it all into the formula here. We're going to get that this integral is equal to x squared times negative cosine of x. I'm going to be smart and just write negative x squared times cosine of x minus the integral of v times du, which is negative cosine of x times 2x dx. If I was really smart, I'd go back and just look at the work I did a few pages ago, because I think we exactly integrated 2x times cosine of x. But pretend like I'm not that smart. Got negative x squared cosine of x. I would, if I had a minus before I started doing another iteration of integration by parts, make it a plus. So I'm going to make that a plus. I'm also going to pull the 2 out in front and have x times cosine of x. And now we're going to do integration by parts again. Here's my new u. Here's my dv. So The nice thing about repeated integration by parts is you can still use the same variables u and dv every time because you're not actually like replacing something. Whereas if you have to do repeated u substitution, which we haven't gotten to yet, then you do have to pick like a new letter for your new u thing, which is annoying. Yeah.
Use B and not just U.
You mean how do I know when to do integration by parts versus u substitution?
Yeah.
So this is kind of what we've been talking about all class. So the way I know how to, and really it's kind of a try a thing. So I tried u substitution here, and I'm usually going to try u sub before I try integration by parts. I tried u sub here because I saw that this choice of u, the derivative of that thing is equal to almost something else I have in my integral. Right? The derivative of x cubed is something times x squared. So that's how I know a u substitution is a good way to proceed, is if the thing I'm choosing for u, its derivative is almost already there. On the other hand, over here, I didn't even consider a u substitution because I knew it wasn't going to work. There really isn't a good choice for u here in the u sub. All right, if I pick u equal to sine, the derivative is cosine. I don't have one of those. If I pick u equal to x squared, oh, here's a really good point. If I pick u equal to x squared, my du is x, and although you might say, James, we have an x, I'd say, no, you don't. You have a sine of x. That x is trapped inside the sine function. It cannot be brought out as just your x times dx. So u sub is definitely not an option here because there's no good choice for u whose derivative is also there. Stepping to the side for just a second. Not every u sub is going to meet that criteria. Sometimes later on, we're going to be forced to do a u substitution where we pick something for u and then its derivative doesn't show up in the integral. And then there's kind of more complicated things we do where we solve for x and find dx, or we do a back substitution, but we're not there yet, so I'm not going to address that just right this moment. But yes, sometimes you don't always get the u sub to work out the nice, perfect way we'd like it to. Continuing on here, u is equal to x. My du is going to be, I usually write dv first, sorry. dv is cosine of x dx. My du is 1 times dx. My v is the antiderivative of cosine, which is sine of x. So then, writing what this is equal to, it's going to be negative x squared times cosine of x still, plus 2 times the entirety, right? That coefficient there times the integral means it multiplies by the entirety of uv minus the integral of v du. So 2 times u times v, so x sine x, minus the integral of sine of x times dx. So let's simplify this a bit. We're going to get negative x squared cosine of x plus 2 times x times sine x plus 2 times negative integral of sine of x. But the negative integral of sine of x is cosine of x. So we get 2 cosine of x. Right, that's going to be cosine of x, and then we're multiplying it by this 2. It gets distributed to each of those things. Let's see. Terrible. And the real terrible thing here is that sometimes they ask you to do it like 3 times. So I'll point out there are 3 types of integrals where you know you're going to have repeated integration by parts. If you have the integral of x to the n times cosine of x, or x to the n times sine of x, or x to the n times e to the x, where n is a positive integer. Each of these requires n iterations of integration by parts. The reason these ones work that way is because the choice for u is going to be x to a power, and every time you choose u equal to x to a power, the derivative is going to be x to the 1 less power. So you're going to have to do n times to get rid of that x to a power. And then the dv thing is a function whose antiderivatives just cycle. The antiderivative of cosine is sine. The antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. The antiderivative of negative sine is positive, right? So they just go through the cycle, or e to the x, right? E to the x just cycles through e to the x the whole time. The good news is there's a shortcut. So there's a shortcut for integrating these 3 types of integrals. And the shortcut is called tabular integration. Literally using a table. So if I was going to try to integrate the same thing I just integrated, x squared sine of x, here's the short, fast way of doing it. What would I pick for u here? X squared or sine of X? Right. So in my U column, I start with X squared. In my dv column, I start with the rest. Except I don't write the dx, so that's annoying. In my u column, since I picked x to a positive integer power, I'm going to take all the derivatives, and eventually the derivative is going to be 0. That's always true for a polynomial. Eventually, if you take enough derivatives, you'll get to 0. Derivative of x squared is 2x, derivative of 2x is 2, derivative of 2 is 0. And then we find the same number of corresponding antiderivatives in our other column. The antiderivative of sine of x is negative cosine of x. The antiderivative of negative cosine of x is negative sine of x. And the antiderivative of negative sine of x is cosine of x. Just to be super clear, we are taking derivatives along the u column. We're taking, use a different color, antiderivatives along the dv column. And then we're almost done. Here's what you do. You take the uppermost u thing and you multiply it by the thing down and over 1. So it's plus that product, minus that product, plus that product. So our answer here would be this integral is equal to x squared times negative cosine of x. I should say plus x squared times negative cosine of x minus 2x times negative sine of x plus 2 times cosine of x plus c. And we can simplify this because we're not barbarians. It's negative x squared cosine of x plus 2x sine of x plus 2 cosine of x plus c. And if we look back at the previous one we just did, it's the same. Right there. Same deal. So if you're faced with something like x cubed e to the x, instead of doing the trash integration by parts 3 times, you can do this tabular integration instead. All right. I could try to squeeze in one more example. Let me say one more thing. Sorry, real quick. So this is just, I think this is kind of cool. How would you integrate the natural log of x? Well, it's integration by parts. And you pick u equal to the natural log of x. What's left to pick for your dv? dv. What's left? Just dx. So dv is dx. du is 1 over x dx. V, the antiderivative of 1, is going to be x. And then writing it out, you end up getting the integral of natural log of x dx is equal to u times v minus the integral of v times du. But 1 over x times x is just 1, and the antiderivative of 1 is just x. So that is how you tackle the antiderivative of the natural log of x. It's also how you tackle the antiderivative of the arctangent of x, is by letting u equal the whole thing and dv equal the dx part that's left over. All right, now I'm really out of time.